Okay, looking into a matrix and its transpose, and we have, let's say if you have a square matrix, like in the case of a 4 by 4 matrix, you had the transpose of a matrix, okay, where we have, say, going from A to B in alphabetical order, and row by row, you have A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. The transpose, okay, you're going to have like the interchanging row and column values. And here we're going to have the transpose. Okay, we have A, E, I, M, B, F, J, N, C, G, K, O, D, H, L, P. Okay, and you can sort of think of like the arrangement, like taking each of the items. So like in the case of what we have for this particular matrix, okay, we have, think of it kind of like moving in clockwise direction: A, E, I, M, B, F, J, N, C, G, K, O, D, H, L, P. And let's say if you have something that is not quite a square matrix, okay, you have the transpose of a matrix, A, B, C, D, E, F, G, H. And for what we have, just like what we had in the first column of one will be in the first row in the transpose, but it also works the other way around. So you can sort of go like counterclockwise. Okay, so you have A, B, C, D, okay, running across row wise. Okay, you have moving vertically downward, okay, in the transpose. So first row, first column, second row, second column, where we have E, F, G, H, E, F, G, H. Okay, so row by row, the transpose of A, B, C, D, E, F, G, H becomes A, E, B, F, C, G, and D, H. And a matrix and its transpose will have interchanging dimensions. And just some of the samples we have here, if I'm looking at the transpose of the following, okay, so we have, like in the first case, we have a 1 by 3 matrix, and the transpose is going to be a 3 by 1. Okay, so you got one row. Well, the transpose is just going to have one column. And, okay, so for the transpose here, so if you have like moving clockwise, you have like 1 at the top, 3 in the middle, and -7 on the bottom. And let's say that for what we have for the second matrix, you got 2, 0, -6, 4, 1, -8. So here we have a 2 by 3 matrix, and the transpose is going to be a 3 by 2. Okay, and so we have for the first row, this would translate to the first column. So you have kind of like, again, just moving clockwise. You have like 2, 0, -6. Again, second row will be the second column in the transpose. So you have 4, -1, and -8. And say if we have, like in the third case, all right, say we have a square matrix, okay, and we have running across, okay, we have first row, we have 1, 9, 10. In the transpose, we have running vertically, same values running vertically, forming the first column. Second row, we have across. In A, we have 5, -2, -6. And the transpose, we want to have second column running vertically, so you have 5, -2, -6. Third row in the matrix A, we're going to have as the last column in the transpose, and so we're going to have 2, 9, and 5. And just looking at what we have, say whereupon, okay, we have for matrix A, okay, here we have a 3 by 4, and the transpose is going to be a 4 by 3. Okay, so we got the first row, and putting this in first column terms, okay, so you have 2, 2, 3, 3. And second row in the transpose, we're going to have second column, so we have 0, 8, 7, 2. And then we have third row in A, we're going to have as the third column. In the transpose, so you have -1, -9, -11, and 12. And just to kind of throw this out, okay, and let's say that if we have, let's say we have 5 by 3, okay, so you have like 1, -1, 0, 2, 7, And see, we have 2, 4, 6, 8, 10. And then we'll see we have -4, 7, 13, -22, and 16. Okay, so this is what we have for A. So we have a 5 by 3. Now the transpose is going to be with the reverse dimensions, and so in this case we have a 3 by 5. Okay, so again, way you can look at this. Okay, so you have in the setup. Okay, so you have a 5 by 3. Transpose is going to be a 3 by 5. Okay, so we have for A we have 1, -1, 0, 2, 7. Say for the first column, and we can make this into the first row in the transpose. So we have 1, -1, 0, 2, 7, and then we have second column. We have 2, 4, 6, 8, 10. And then we have last column in A will be the last row in the transpose. Okay, and so you have the transpose of A is going to be A of T, and guess what? The transpose of the transpose gets us back to the original matrix A. All right, and for what we have regarding special cases of what we have regarding transposes, and we have with rules of thumb here. There are various types of matrices, and most are not going to be symmetric. Okay, but in the case of those that are, a matrix is regarded as symmetric whenever the original matrix A and its transpose turn out to be the same. And guess what? As an example, we have A consisting of row by row 2, 4, 6, 4, 3, 0, 6, 0, 1. And guess what? Converting like the row values into column values, kind of going in the clockwise direction. Okay, so you got 2, 4, 6, 4, 3, 0, 6, 0, 1. And so we have an identity between the matrix and its transpose, and so in this case A is regarded as symmetric. Now the other category is if you have a matrix and its transpose to be consisting of additive inverse elements, then the matrix is regarded as skew symmetric. Okay, and the transpose would also be regarded as skew symmetric. Okay, so we have for A, okay, got 0, 3, 0, 6, -3, 0, -4, 0, 0, 4, 0, -5, and 6, 0, 5, 0. And guess what? If I take the transpose, first row, first column, 0, -3, 0, 6, 3, 0, 4, 0, 3, 0, 4, 0. And we got 0, -4, 0, 5, 0, -4, 0, 5, -6, 0, -5, 0, -6, 0, -5, 0. And guess what? For the non-negligible values, you got 3, -3, -6, 6, -3, 3, -4, 4, and you have 4, -4, -5, 5, and then we have 6 and 5 in the last row of matrix A, and you have -6, -5 in the last row of the transpose. And guess what? We have an additive inverse relation, and therefore, okay, we have A to be regarded as skew symmetric.